Hello, our topic for today is about limits of trigonometric functions. These functions are uh, containing the trigonometric functions such as sine, cosine, tangent, cosecant, secant, and cotangent. Okay, and for before we deal with some problems or evaluate some problems containing these trigonometric functions, now I do advise everyone to be familiar or to familiarize the graphs of these six functions, okay, uh, where especially the points of intersection among the or the points of intersection in the x and y axis of the rectangular coordinate plane, because once we see or we understood or we familiarize with the behavior of the graphs of these six functions or trigonometric functions, then we can easily illustrate and visualize, okay, the limits of the functions at a certain number or at a certain point. Okay, so we have this one is the graph of sine function where it passes through the origin, all right? And here, yeah, this is the graph of cosine where it passes through the y-axis at 1, where the maximum and the minimum values or range, values of the range are equal to 1 and -1, okay? Where the range is from -1 to +1, as well as the sine function, okay? And for the tangent passes through at the x or at the origin as well, and it has infinite number of asymptotes, and one of them is pi over 2. Okay, pi over 2 because the cosine becomes 0. All right, because we know that tangent is equal to sine over cosine. So for it to have a an asymptote or a vertical asymptote, the denominator must be equal to 0. And for that to be equal to 0, it should have, or the cosine, okay, the cosine in tangent should be equal to 0. All right, that's why its asymptote is at the uh, point x over 2 of the x-axis. Okay, and for the cotangent, this is the graph, the cotangent. It's just like the reverse of the graph of the tangent, but it doesn't pass through the origin. And also, the the vertical asymptote of the tangent, or one of the vertical asymptote of cotangent, is at x is equal to 0. All right. And for the cosecant graph, now its asymptote is x is equal to 0. Okay, and for the secant, it passes through the y-axis at 1. Okay, and its asymptote is equal to pi over 2. All right, pi over 2 and others, because there are infinite number of vertical asymptotes here. Okay, and let's apply, let's use the theorem in solving trigonometric functions, okay, or finding the limits of trigonometric functions. Now, but before we solve, let's deal with the theorem number 1. Theorem number 1 states that let C be an element of domain f of x, where f of x is a trigonometric function, then the limit of f of x, okay, as x approaches c is just equal to f of c, which means that as long as c is part of the domain of the trigonometric function, okay, then we can just substitute the value of x, which is c, to the given function for us to solve for the limit of the given function. So for example, we have when x is equal to 0, since 0 is an element, okay, of the function, let's say sine x, then we could say that the limit of sine x as x approaches 0 is just equal to substituting 0 to the variable x of sine is equal to 0, okay? Because sine 0 is equal to 0. So that's what the theorem tells about, okay? Okay, so now let's deal with problem number 1, which is the limit of sine x as x approaches 2 pi over 3. Now here, we know that 2 pi over 3 is an element of the function sine x, okay? So it is one of the domains or values of the domains of the function sine x, because we know that in a sine, okay, in sine function, now in sine function, sine, the domain of sine function is equal to all real numbers. So whatever value of x here, okay, then we're just going to substitute that value to find the limit of the sine x, all right? So 2 pi over 3 can be found, okay, 2 pi over 3 can be found here. That's 2 pi over 3, okay, 2 pi over 3. And we know that this point has values, okay, which are real numbers. Therefore, we know that x, the value of x, which is 2 pi over 3, is still part of the domain of sine x, all right? And the values of x and y here are not undefined or indeterminate in form, okay? So we're just going to substitute the values of x, which is 2 pi over 3. So to get the limit of sine x as x approaches 2 pi over 3, we're just going to substitute that. This becomes 2 pi over 3. And for us to solve for this, we can use the unit circle, all right? Or we can also use the graph of sine x to solve for the value of sine 2 pi over 3. We know that 2 pi over 3, this is equivalent to 120 degrees. If this is 120, this is 60. So we have a right triangle. Okay, so we have a right triangle here. If this is 60, this is 30. Okay, and if this is 1, this is 1/2. And this is square root of 3 over 2. And since sine is saw, which is opposite over adjacent, opposite over hypotenuse, so that's square root of 3 over 2 over the hypotenuse, which is 1, is equal to square root of 3 over 2. Okay, so therefore the limit of sine x as x approaches 2 pi over 3 is equal to square root of 3 over 2. So in substituting the value of x, or direct substitution of the values of x set in the given problem, as long as they are part of the given domain of the given function, okay, then direct substitution is allowed. And we can use the unit circle or even the graph of the given function, okay? So I hope we get the same answer. And let's work on problem number 2. So our trigonometric function here is cosine x, and x approaches pi. And we know that pi is an element of the domain, okay, of the domain of cosine x, the domain of the cosine x. So therefore, we are allowed to substitute pi to the x of cosine, or we can use direct substitution. So we have the limit of x cosine x as x approaches pi is equal to, we have pi to the x and cosine pi. Okay, so I'm using red. And here, we need to find the value of cosine pi, and we know that pi is here, this is pi, okay? And the point here is negative 1, 0. So if we have a circle here, this is the pi. All right, this is pi. Okay, the angle formed is pi. And cosine pi, which is the value of x in the given point, okay, that's negative 1. So this becomes negative pi. That's why the answer here is negative pi. Okay, so the limit of x cosine x as x approaches pi is equal to negative pi. All right, and I hope we got the same answer again. So in theorem 2, it says, suppose the limit of the function g as x approaches c is equal to k, where k is an element of the domain f of x, where f of x is a trigonometric function, then the limit of f of g of x as x approaches c is equal to f of k. So in this theorem number 2, it uses the theorem number 1, the one that we discussed a while ago. So as long as k is part of the domain of the trigonometric function in the given, then we can substitute that value to the given function f. All right. So let's apply this theorem in the given example. So let's have limit of secant 1 over x. Let me change the color. Okay. So as x approaches infinity, so here we're going to test or check whether once we substitute infinity to 1 over x, we're going to check if it will be still be part of the domain of secant. All right. So here, let's go. So what we can do is secant 1 over infinity. Let's check. And 1 over infinity is equal to 0, right? So 0. Now let's check if 0 is an element of the domain of secant x. Okay? Now we know that secant is 1 over cosine 0 or cosine x, let's say. And if x is equal to 0, then cosine x or 0, sorry, let me erase that. Okay, cosine 0, this is 1 over, cosine 0 is equal to 1, so which is equal to 1. Since the result is not undefined, all right, or it does not result to indeterminate value or indeterminate in form, then we could say that we can substitute 0 to we can substitute the infinity, all right, to the inner function 1 over x in the given problem. So here, for us to solve for the limit, we have secant 1 over infinity, which is equal to secant 0. And secant 0 is equal to 1 over cosine. If you're having a hard time or difficulty in evaluating this, you can convert it to a basic trigonometric function, cosine, sine, or whatever. Okay, whatever applies. So I know that cosine 0 is equal to 1, so therefore the answer here is 1. Okay, so the limit of secant 1 over x as x approaches infinity is equal to 1. Okay, so let's deal with problem number 4 and try to answer this on your own. And let's see if we'll get the same answer. So our x here approaches square root of 2. Now let's check if it satisfies the given condition in a given theorem number 2. Okay, so we have tangent, okay, pi times x squared, oh sorry, x squared minus 1. Since our x approaches square root of 2, let's substitute that here. Pi square root of 2, that's 2 minus 1. Okay, so this becomes tangent pi. Okay, and we know that tangent pi is equal to sine pi over cosine pi. All right, and we know that this the pi here, or this expression, will not result to undefined or indeterminate in form. So how? Okay, let's try it. Sine pi is equal to 0, and cosine pi is equal to -1, which result to 0. So since 0 is, let's discuss this first. Since pi is part of the domain of tangent, therefore, we can substitute square root of 2 here. And also, since tangent pi is equal to 0, and 0 is also part of the domain of sine, so we can definitely substitute square root of 2 in x here, okay? So let's do that. So we have sine of the tangent square root of 2 square minus 1 pi is equal to sine tangent square root of 2 minus 1 times pi. And this is sine tangent pi. And we know, we have already solved it, that sine tangent pi is equal to 0. So we have sine 0 is equal to 0. Okay, why 0? Because 0 degree, okay, let me use another color. 0 degree or 0 radian is here, and the point here is 1, 0, right? So sine means y, so therefore the y here is 0. That's why the answer is 0. So I hope we get the same answer as well. Okay, let's go to number 5. Number 5, the limit of cotangent x as x approaches 0 from the right. So here, now we want to check if 0 will be or is part of the domain of the function cotangent, okay? For checking, let's deal with cotangent x. I know that cotangent is equal to cosine x over sine x, right? Okay, so in this case, we can check, or we can substitute the value of x here, which is 0. We could have cosine 0 and sine 0. So this becomes cosine 0 is 1 and sine 0 is 0, okay? And 0 is part of the domain of sine, all right? And here, this becomes infinite, all right? Infinity, I mean. And since it's all the values 0, I mean, all the values from the right of 0, it means those are positive values. So which means that sine 0 are positive numbers. So therefore, this is positive. Okay, that's why the limit of cotangent x as x approaches 0 from the right is infinity positive. Okay, undefined. Okay, so it is increasing, increasing as x approaches 0 from the right without bound. Okay, next, number 7. So let's solve this. Okay, let me just change the color. Okay, now let's simplify. So the limit of 4 minus 4 sine x all over 3 cosine square x as x approaches pi over 2. We know that pi over 2 is a part of the domain of sine and cosine, so we can substitute pi over 2. So let's simplify first. This is 1 minus sine x. We factored 4. This becomes 3 cosine square x as x approaches pi over 2. And here, cosine square x is, or can be convert converted into sine, all right, or it can be written in terms of sine. So we can use the identity of cosine square, which is 1 minus sine square x. So that's 4 1 minus sine x over 3 1 minus sine square x. All right, and let's simplify this. Oh, as x approaches pi over 2. Now, the denominator can be factored into 1 minus sine x times 1 plus sine x. So let's do that. The limit of 4, 1 minus sine x over 3, 1 plus sine x times 1 minus sine x. Okay, so these are the factors of the denominator, and we can cancel out this. So this is 1, this is 1, as x approaches pi over 2. And this becomes the limit 4 over 3, 1 plus sine x. Okay, as x approaches pi over 2. And then again, pi over 2 is part of the domain of sine x, so we can do direct substitution. So let's change to white. So let's do direct substitution. 4 over 3 times 1 plus, what is sine pi over 2? That's 1, right? Okay, so this becomes 4 over 6, which is 2/3. So the limit of this function is equal to 2/3. Okay, and I hope we got the same answer. Now let's work on number 8 and try to solve this on your own. And let's see if you'll get the same answer. All right, so let's solve. Limit of sine 2x over sine x as x approaches 0. So in this problem, we can use another identity of sine 2x. Sine 2x, all right, sine 2x is equal to 2 sine x cosine x. All right, how did we get that? Because sine x plus x is equal to sine x cosine x plus cosine x sine x is equal to 2 sine x cosine x. So that's how we got 2 sine x cosine x. So let's substitute that here. So the limit of 2 sine x cosine x over sine x as x approaches 0, we can do cancellation here. We can cancel out sine x. So we will cancel sine x and sine x. So this becomes 1 and 1. And this becomes limit of 2 cosine x as x approaches 0. And since 0 is part of the domain of cosine x, therefore, we can do direct substitution. So that's cosine 0. And 2 times cosine 0, 2 times 1 is equal to 2. That's why the answer here is 2. Okay? And again, I hope we got the same answer. All right, so let's move on to the limits of trigonometric functions part 2. Here, we will be applying another theorem for us to solve some more complex trigonometric functions. Now, theorem number 1 states that the limit of sine x over x as x approaches 0 is equal to 1, and the limit of x over sine x as x approaches 0 is equal to 1 as well. Now, considering the first theorem, how do we show that this second equation is true? Okay, so let's use the first theorem. So the limit of sine x over x is equal to 1. approaches 0. Okay, so we will be solving for this. So that's the limit of x over sine x as x approaches 0. So this could be rewritten in a form of, or by reciprocating the, okay, the numerator and denominator, the expression. So we have sine x over x raised to -1 as x approaches 0. All right, so here we can take the limit of the inner function, which is sine x over x. So that's the limit of sine x over x as x approaches 0 raised to -1 is equal to, the limit of this is equal to 1 based on uh, the first given in the theorem number 1. So this is 1 raised to -1 is equal to 1. That's why it's equal to 1. Okay, so even if the x and the sine x interchanges position, the limit of that expression is still 1 as long as x approaches 0. All right, so let's apply this theorem. The limit of sine 3x over x as x approaches 0. So in this case, we need to make sure that the denominator, okay, of sine 3x is the same as the number of the given, or the angle measure of the given trigonometric function. So here, it needs to be, or for us to apply the theorem, the denominator should be 3, all right? Or should be 3x. Now, for it to be 3x, we lack 3 on the denominator. So what we need to do is to multiply the given expression sine 3x over x by 3 over 3. Okay, so it's same as multiplying it by 1. Okay, so we have the limit of sine 3x over 3x, all right, times 3 as x approaches 0. So since this is a constant, then we can use the property of limits. This becomes 3 times the limit of sine 3x over 3x as x approaches 0. And this becomes, based on the given theorem number 1, this just equal to 1. So which makes it equal to 3. Therefore, this is equal to 3. Okay, so I hope we got the same answer. And let's work on problem number 2. So in problem number 2, it's limit of tangent x over 2x as x approaches 0. Now here, uh, we can, for us to use the theorem number 1, we can convert tangent to sine and cosine function. Okay, so we have, or if we're going to do a direct substitution, all right, since 0 is part of the domain of tangent x. Now what we will get, tangent 0 over 0 is equal to, what is tangent 0? That's 0 over 0, which is an example of indeterminate in forms, which means we need to do something to simplify, okay, to evaluate the limit of tangent x over 2x as x approaches 0. So what do we need to do? Let's decompose or express tangent x into sine and cosine. So this becomes limit of, we have sine x over cosine x times 1 over 2x as x approaches 0. Okay, since the numerator is sine x, then we can use the theorem number 1, okay, by placing x on its denominator. So we have a limit of sine x over x, and we have 1 over 2 cosine x. as x approaches 0. So in this case, we can take the limit of the factors. So the limit of sine x over x as x approaches 0 times the limit of 1 over 2 cosine x as x approaches 0. So we're going to take the limit of two factors. Now, the limit of sine x over x as x approaches 0 is equal to 1 based on theorem number 1. And the limit of 1 over 2 cosine x as x approaches 0 is, since 0 is part of the domain of cosine x, so therefore we can do direct substitution, right? So we have 1 over 2 cosine 0. So this becomes 1 over 2. What is cosine 0? Cosine 0 is equal to 1. And this results to 1/2. So the answer is 1/2. Okay. And I hope we got the same answer again. So let's work on number 3. In number 3, it says here the limit of tangent of x minus 5 over x squared minus 6x plus 5 as x approaches 5. So we can do direct substitution here since 5 is or will result to a part of the domain of tangent, right? So let's try substituting. So this becomes 2 tangent 0 over what's this? This is equal to 25 minus 30 plus 5. And tangent 0 is equal to 0. 2 times 0 is 0. And 0. So this is an indeterminate form, so we need to work on something for us to simplify or evaluate the limit, right? So we have, let's copy the limit, and we can place the 2 as the coefficient of the limit expression since it's constant. So we have, let's convert tangent to sine and cosine, okay? Let's express tangent in terms of sine and cosine. So we have 1 over, sorry, let me just, okay, let's, oops, there we go. So sine of x minus 5 over cosine x minus 5. And the denominator can be factored into x plus, oh sorry, x minus 5 x minus 5 and x minus 1, right? Okay, so now the degree or the angle measure of sine x or sine function is x minus 5. So we need to place x minus 5 on the denominator of the sine for us to use the theorem number 1. So as x approaches 5, so this becomes 2, oops, sorry. Okay, so this becomes 2 times the limit of sine of x minus 5 over x minus 5 times 1 over x minus 1 times cosine of x minus 5. Okay? So we have already expressed this in terms of the theorem number 1. So we have, oh, okay, so let's write our next part of the solution here. So this becomes 2. We can take the limit of this. Okay, so I forgot. X approaches 5. We can take the limit of the first factor, which is equal to 1, times the limit of 1 over x minus 1 cosine x minus 5. Sorry, I put cosine in this manner because it can't, I can't write x minus 5 in this area. So as x approaches 5, okay? So we have, let's simplify. We have 2 times 1 is 2. And what is the limit of x minus 5? Oh, sorry, what? It's supposed to be x minus 1. Yeah, x minus 1 times the limit of this second factor. We can do direct substitution, okay? For x, I mean for the value of x, which is 5. So 5 minus 1 times cosine 0. So this becomes 2 times 1 over 4 times cosine 0 is equal to 1. So this is equal to 1 half. 1 half. Right, so 1 half because 2 times 1/4 is 1 half. So therefore, our answer is 1 half. Okay? And again, I hope we got the same answer. And I hope you understood what I wrote here on this side. Okay. In theorem number 2, the limit of 1 minus cosine x all over x as x approaches 0 is equal to 0. And the limit of cosine x minus 1 all over x as x approaches 0 is equal to 0. So here, we're going to apply this theorem. Let's apply this theorem number 2 in solving problems, like evaluating the limits of trigonometric function. Using theorem number 2, let's evaluate the limit of 1 minus cosine x all over sine x as x approaches 0. So in this case, for us to solve this, we need to express it similar to the one we have in theorem number 2. So what we do is we copy the numerator, and based on the given theorem, 1 minus cosine x all over x as x approaches 0 is equal to 0. That's what we have in theorem number 2. So if we're going to place this x in the denominator, of course, we need to place x also on the numerator for us to set the given expression same as the original one, okay? Over sine x. Okay, as x approaches 0. So here, we can take the limit of each factor. So 1 minus cosine x all over x as x approaches 0 times the limit of x over sine x as x approaches 0 as well. So the first factor, and this is equal to 0 based on the given theorem number 2. And the second factor is limit of x over sine x as x approaches 0. This is equal to 1 based on theorem number 1, which results to 0 times 1 is equal to 0. So the answer number 5 is 0. Okay, and I hope we got the same answer again. And for item number 6, we have this function. And let's apply theorem number 2. And even theorem number 1 if good. Okay, so I have sine x cosine x here, and 1 minus cosine x. So I know in theorem number 1, sine x over x limit as x approaches 0 is equal to 1, and the limit of 1 minus cosine x as x approaches 0 is equal to 0. So we can, I think we can use both theorems 1 and 2 to solve number 6, since we have sine x and 1 minus cosine x. So let's rewrite the problem. So we have sine x over x, since it's x squared, 1 minus cosine x over x. And there's a cosine x remained here. There we go. As x approaches 0. So this expression is the same as the original problem. So we have this, and we can take the limit of each factor. So the limit of this is equal to 1. The limit of this is equal to 0. And the limit of cosine x as x approaches 0 is equal to 1. However, 1 times 0 times 1 is equal to 0. So the answer number 6 is 0. Okay, and in number 7, try to solve this on your own as well. Again, and let's see if you'll get the correct answer. All right, so how do we solve this problem? Okay, so the limit of sine x over x plus sine x as x approaches. So in number 7, there are two ways to solve for the limits of this expression or function. So let's have method 1. In method 1, I need to express this function, given function, as sine x over x, all right? And for me to do that, I can take the reverse of the given expression. So I have x plus sine x over sine x. And of course, since we take the reciprocal, let's take the raised to negative 1. Okay, this puts this expression back to its original form. All right, so we can now simplify this. So I can have the limit as x approaches 0. I can simplify this, x over sine x plus sine x over sine x is equal to 1 raised to negative 1. And I can now take the limit. So I have the limit of x over sine x as x approaches 0 plus the limit of 1 as x approaches 0 raised to negative 1. So let's take the limit term by term. So the limit here is equal to 1 based on theorem number 1, plus the limit 1 as x approaches 0 is equal to 1 raised to negative 1. So this becomes 2 raised to negative 1 is equal to 1/2. So the answer is 1/2. Okay, and let's take another method to solve this. So in number 7, the problem is sine x over x plus sine x as x approaches 0. So what I can do here, I can divide both numerator and denominator by sine x, all right? Or multiply numerator and denominator by 1 over sine x. So let's multiply. Here we go. So we have the limit of 1 over x plus sine x over sine x as x approaches 0. And this becomes the limit of 1 over x over sine x plus 1 as x approaches 0. And then again, we can take the limit of all the terms. Okay, so we have the limit of 1 as x approaches 0 over the limit of x over sine x as x approaches 0 plus the limit of 1 as x approaches 0. Okay, so the limit of 1 as x approaches 0 is 1. The limit of x over sine x as x approaches 0 is 1. And the limit of 1 as x approaches 0 is also 1. So this becomes 1 over 2, so 1 half. And we get the same answer as the one we have in method 1. So which means our answers are correct. And I hope we get the same answer. And again, if you have some questions, please do comment under this video. Thank you, and I hope you learned a lot.